The theory of relativity provides a way for observers to agree on what they see from different perspectives. The perception of an object can vary from situation to situation or from person to person. For example, objects up close appear to be larger than when further away. Furthermore, objects traveling in a moving car appear to be at rest relative to the observer in the car. An observer on the side of the road, however, perceives the objects moving at the same speed as the car itself. In other words, while the objects in the car are not moving relative to the car, they are moving relative to the road. Now, classical relativity tells us that motion is relative to the observer's state of motion. But here's a question. Is all motion relative to the observer's state of motion, as classical relativity would suggest? Well, it appears the answer is no. Classical relativity breaks down at really high speeds. For example, the speed of light. Several observations and numerous experiments have shown that light travels at the same velocity regardless of the observer's perspective. Whether the observer is standing still or moving, the speed of light appears to be the same. The speed of light is 186,283 miles per second, or 299,792 kilometers per second. And we abbreviate the speed of light with the letter c. Now, to make our math easier, we're going to consider the speed of light to be 300,000 kilometers per second. The speed of light is c, and it's c regardless of the source of the light or the perspective of the observer. Let's look at an example. Imagine you're traveling away from the sun at a velocity that's really close to the speed of light. Let's say 250,000 kilometers per second. That's pretty fast. And let's have some fun with this and say you can see a photon of light moving away from the sun and passing you up through some window in your spaceship. Now, get out your trusty radar gun and measure the speed of light as it passes by the window. What would the speed of light measure relative to your ship? Well, based on classical relativity, you might predict the velocity of the light relative to your ship to measure 50,000 kilometers per second. As your ship is already traveling 250,000 kilometers per second, and 300,000 kilometers per second minus 250,000 kilometers per second is 50,000 kilometers per second. However, you would measure the speed of light to be 300,000 kilometers per second. Don't buy a new radar gun just yet. As it turns out, your radar gun is correct. The speed of light is the same relative to your fast-moving ship or even an external stationary point. Now let's say you shoot a laser of light away from your spaceship. Using your trusty radar gun, you would measure the speed of the laser to be 300,000 kilometers per second. Let's say your buddy has the same radar gun on Earth. How fast would she record the laser of light to be moving? You guessed it. Your buddy would measure the velocity of 300,000 kilometers per second. As you see, the speed of light is the same relative to your fast-moving spaceship as it is relative to your buddy standing still on Earth. The speed of light is not relative. Well, we need to reconcile this apparent inconsistency of light speed with the theory of relativity, at least classical relativity. Is it possible for speed to be both relative to the perspective of the observer and constant when it comes to really fast-moving speeds, such as light? Albert Einstein, perhaps the greatest physicist of the 20th century, proposed that both indeed are true. He proposed that a person traveling at a constant velocity will observe the same laws of physics as a person at rest. Speed is a measure of distance traveled over time. You know, this is true for light as well as it is for any other object in motion. Since light follows the laws of physics, Einstein postulated that all observers will measure the same speed of light regardless of their state of motion. In other words, light will travel at the same distance in the same amount of time. We can understand Einstein's proposal by breaking down speed. Speed is simply a measure of distance traveled over time. In fact, we use the term light year to express the distance traveled by light in 1 year. The formula for speed is s equals d divided by t, where s is speed, d is distance traveled, and t is the time required to travel that distance. According to this formula, if both distance and time change by the same factor, speed does not change. For example, one car traveling 10 miles in 1 hour and another car traveling 100 miles in 10 hours will both travel at a speed of 10 miles per hour. Their speed is the same. Likewise, different observers can agree on the same speed of light if they disagree on distance and time. And as it turns out, both distance and time are relative to speed. At very fast speeds, say the speed of light, time slows down and distance shortens. This allows both stationary and moving observers to record the same speed of light. But how does time slow down? And how does distance contract at high speed? These phenomena will be explained in subsequent lessons. In summary, the theory of relativity provides a way for observers to agree on what they see from different perspectives. Classical relativity tells us that motion is relative to the observer's state of motion. However, classical relativity breaks down at the speed of light. The speed of light is not relative, but rather is always measured at 300,000 kilometers per second, and that's regardless of the source of the light or the perspective of the observer. Einstein proposed that observers may have to disagree on distance and time in order to agree on the speed of light. Now, if speed is a measure of distance over time, speed can remain constant if distance and time change by the same magnitude. And science has demonstrated that both distance and time shorten at really fast speeds. This allows the speed of light to be the same, regardless of its source or the perspective of the observer. Therefore, distance and time are relative to speed.